Dedup gets dangerous when your threshold silently hides good documents or keeps noisy copies. I will tune MinHash LSH with datasketch in Python so you can see the real trade-offs. This is the pattern you'll be able to implement by the end, which tunes a near duplicate cutoff from labeled pairs and deduplicates documents while reporting recall and precision. I'm Professor Pi, teaching search and IR with simple Python. Many search teams hit dedup as a practical bottleneck. Duplicate pages waste user time and indexing budget. But if you merge too aggressively, you lose unique content. MinHash with locality-sensitive hashing, or LSH, is a common way to find near duplicates at scale. It is fast and memory-friendly compared to pairwise comparisons on large corpora. We will use the datasketch library because it gives MinHash sketches and an LSH index out of the box, which saves us building complex hash tables from scratch. At a high level, MinHash turns token sets into compact sketches that preserve Jaccard similarity. If two texts overlap a lot, their sketches will appear similar. LSH groups sketches, so you only compare promising candidates, not every pair. The trade-off is tuning thresholds. Too low and you get many false positives. Too high and you miss true near duplicates. Next, we will build a tiny pipeline that demonstrates a labeled tuning loop and a confirm step before merging. This keeps the code friendly and the idea portable to larger projects. Now we'll create two simple MinHash sketches and check their similarity. This snippet estimates near duplicate similarity between two texts using datasketch MinHash. Two short strings, A and B, simulate a near duplicate pair that differs by one extra word. The variable M1 and M2 are MinHash sketches with 64 permutations and a fixed seed to keep results deterministic. The update batch call feeds each unique token, encoded as bytes, into its sketch, so that the Jaccard estimator becomes available. Finally, the Jaccard method on MinHash returns the similarity estimate between the two sketches. Increasing numperm typically reduces variance, but costs more memory and time per sketch. The printed estimate shows whether MinHash captures the high overlap that near duplicates should exhibit. Now we'll index a handful of documents and query for candidates. This example builds a datasketch MinHash LSH index and retrieves candidates for one document. The dictionary docs contains 5 short texts that mix similar and dissimilar content. The function MH creates a MinHash sketch per text using 64 permutations and a stable seed. The MinHash LSH object LSH is configured with a 0.6 similarity threshold and receives each key and sketch via insert. A query for the sketch of document A returns candidate keys likely to be near duplicates. Lowering threshold typically boosts recall but can add false positives. Raising it prunes candidates but risks misses. The printed candidates confirm that the LSH index surfaces the most similar texts to a. Next, we will compute exact Jaccard pairs to form a gold set and compare LSH output. This code scores the LSH output against an exact Jaccard gold standard. The variable tTrue sets the true duplicate cutoff at 0.7, which defines the set true of correct pairs from all document combinations. The set pred is built by querying LSH with each document sketch created by MH and collecting unique candidate pairs. Intersecting pred with true yields true positives TP, which drive precision and recall calculations. This isolates whether your LSH threshold is too permissive or too strict for your dedup needs. Increasing tTrue makes gold labels stricter and usually lowers measured recall. The printed precision and recall show how well LSH matches your desired duplicate definition. Now we will sweep LSH thresholds to see how recall and precision move. This snippet sweeps MinHash LSH thresholds to visualize recall trade-offs. The function score builds a fresh datasketch MinHash LSH with a given threshold th, inserts all document sketches via insert, and gathers predicted pairs through query. It then intersects predictions with the gold true set and returns precision and recall. The two calls test a permissive threshold, 0.55, and a stricter one, 0.75, against the same ground truth at 0.7. Lower thresholds tend to increase recall, while higher thresholds reduce misses only if the data truly clears that bar. The printed recall values reveal how sensitive your pipeline is to the LSH threshold. Finally, we will add a cheap exact confirm step to remove false positives from LSH. This example hardens the LSH pipeline with a confirm step using exact Jaccard. The variable confirm sets a stricter acceptance threshold, and filt collects only those LSH candidate pairs whose exact overlap meets or exceeds it. The LSH.query results are rechecked with token set Jaccard, so borderline pairs get filtered out before merging. This two-stage design keeps LSH fast while avoiding quality regressions from false positives. Raising confirm improves precision, but may drop recall. Lowering it boosts recall while risking more bad merges. The printed precision and recall show how confirmation recovers reliability without sacrificing your target recall. This toy flow maps easily to a real pipeline. Replace the 5 sample docs with your corpus and persist sketches for online dedup checks. Use the same two-stage idea on top of an ANN index for larger collections. Recap: MinHash LSH turns sets into sketches so you avoid all pairs comparisons. Tune the LSH threshold when you care about recall versus noise. Add an exact confirm step when precision matters. Next step: run a threshold sweep on your actual labeled pairs and pick the LSH threshold that gives your target recall. Then test a confirm cutoff to recover precision. If short, practical IR helps, subscribe and watch the IR videos.